All right, so here's the example we left off on in the last example, or in the last video. It may be worth, just to kind of convince yourself that we've done what we set out to do, to take the original matrix A and multiply it on the left and on the right by this matrix that we found, to show that in both cases you end up with the identity matrix. I'm not going to do that here, but it's a good exercise just to help yourself be convinced that what we did worked. But now we're going to go ahead and move on to this theorem. So this theorem states that if A and B are both invertible matrices, and if they have the same dimensions, so they both be n by n, whatever that is, and if the product then the product of A times B is invertible, and in fact we have a way of directly finding that inverse. The inverse of the matrix AB is equal to the inverse of B times the inverse of A. In other words, you reverse the order of these matrices and make them inverses. Okay? So this is an important theorem, and later on, we can't do this quite yet, but later on we're going to prove the converse of this, which is really, really important. So the converse of a theorem, if you have a theorem of the form if P then Q. So if this property, then this property. The converse of that theorem reverses the role of P and Q. If Q, then P. So the converse would say if AB is invertible, then A and B are also invertible. We don't get to use that theorem yet because we can't prove it yet. We have to develop a little bit more tools in order to get there. So for now, we're just going to prove this. How do you prove that a matrix is invertible? Well, again, remember, we're going to develop a whole lot of different criteria to show that, but right now we can just use the definition of invertibility. Not only am I suggesting that AB is invertible, but I'm giving a candidate for its inverse. So we can simply take the matrix AB, multiply it on both sides by this, B inverse, A inverse, and show that in both cases we end up with the identity. And I'm doing that here. I'll let you look at the steps here to make sense of it. It's a good exercise to make sure you understand how we're getting from each step to each step. But notice the associative property, getting from here to here, for example, or from here to here, is playing an important role in these proofs. So knowing that matrix multiplication is associative is very, very valuable in getting us the results that we're getting here. Okay, but remember this theorem, we're going to use that in the future. All right, so let's think for a moment about the operations that we've defined for matrices. We've defined addition and subtraction. We've defined two different kinds of multiplication. There's multiplication by a scalar, and then there's multiplication by another matrix. We said that there really is no operation of division for matrices, not a general one anyways, so we can't really talk about dividing two matrices. But it kind of makes sense that if you wanted to, if we're able to multiply matrices, then perhaps we would also be able to raise matrices to powers, since exponents are really just repeated multiplication. And it turns out we can do that, but only if the matrix is square. And if you think about it for a moment, you should be able to see why that's the case. If you have a non-square matrix, then multiplying that matrix by itself would not be defined. The dimensions won't match up correctly. But if A is a square matrix, then you can multiply A to itself repeatedly, and we define exponents the way you would expect. A to the power of n, if n is a positive integer, is just the product of A with itself n times. Okay? Now, when you learn about exponents in, I guess it would be, upper elementary school typically, where we first start talking about those, you gradually develop the idea of exponents to include more than just positive integers. So you start with positive integers, which represent repeated multiplication. Then you say if you raise a non-zero number to the power of 0, that's equal to 1. If you raise if you raise a number to a negative integer exponent, then that negative in there represents a reciprocal, and then you can take that reciprocal and then use repeated multiplication from there. And then you go on and you define rational exponents and all those other things. We don't want to go that far with it, but we do want to talk about what it could mean to raise a matrix to a negative exponent. mimicking what we do with real numbers. Remember, in real numbers, that negative represents a reciprocal. And for us, the analog of the reciprocal of a real number is the inverse of a matrix. So we can only take negative integer powers of matrices if that matrix is invertible to begin with. But if that's the case, then we define a to the negative n power to be the inverse of a raised to the n power. Notationally, that's what this represents. And then, again, just like in the real numbers, if you raise a non-zero real number to the power of 0, then we define that to be 1. Here, the analog would be defining a matrix to the 0 power to equal I, the identity matrix. Okay? So, with that idea, with that notation, it shouldn't be too difficult to see that some of the familiar properties of exponents when we're talking about real numbers carry over to the case of matrices. In particular, you have this property. If you have if A is a square matrix, you have A to the power of R times A to the power of S. This would be the same thing as A to the power of R plus S. Very easy to see why that's the case. Similar here, A to the power of RS is equal to A to the R, all to the power of S. Again, the proofs of both of these would look identical to how you prove these properties for real numbers. There's nothing fancy going on there. We can establish more useful properties of exponents in this theorem here. So if we assume that A is an invertible matrix, and if n is a non-negative integer, then A inverse is invertible, and the inverse of A inverse is A. This is easy to show because, again, remember, this is saying we have this matrix that we're calling A inverse. Its inverse should be a matrix that can be multiplied to A inverse and give me I. But by definition, A inverse times A gives me I. So that establishes that pretty easily. In fact, here's a little bit more careful of a proof of that down here. You can kind of read through that. B, if A to the nth power is invertible, if A is invertible, then A to the nth power is invertible, and its inverse looks like this. It's the inverse of A raised to the n power. Another one that's easy to prove, and we're going to omit the proof here. This final one here is proven in your book. If A is invertible, then any scalar times A will produce another invertible matrix, as long as K is a non-zero scalar. And the inverse of Ka will be the inverse of K times the inverse of A. Now, when I say the inverse of K, remember K is a scalar. So literally when I say inverse, I mean reciprocal. 1 over K times the inverse of A. Check out the proof in your book. These are all really straightforward to prove. They're not hard to wrap your mind around, I think. So now that we've defined exponents for matrices, in algebra, exponents show up in a number of places, but primarily when we're dealing with polynomials. And so it seems kind of natural that we could provide a connection between polynomials where the variables represent real numbers and polynomials where the variables represent matrices, square matrices in particular. So if we have a polynomial, p of x equals this, a naught plus a1x plus, this is an nth degree polynomial, so we go out to this x to the nth power term, and all of these are real coefficients, then plugging a square matrix A into this polynomial represents this. Now notice we could plug A directly into all of the x's, because if A is a square matrix, then we can raise A to any one of these powers. So A1A, A2A squared, and so on. How do you deal with this constant term, though? Because remember, if A is an n by n matrix, then all of these terms from here onward would be n by n matrices. But A naught is a scalar. You can't add a scalar to an n by n matrix, or any matrix for that matter. They're not compatible for addition. So we need to turn this constant into another n by n matrix, and the natural way to do it is to multiply it to the identity. And the reason for that, again, is because the identity functions like the number 1 in the real numbers. A naught times 1 is the same thing as A naught. It's the most natural thing to put there. So let's evaluate a quadratic polynomial for a particular square matrix. Now, what I'm going to do is begin with just this term right here. So my x, let's actually do this. P of A, let me write an A in there, is equal to 1103 squared minus 2 times 1103 plus, now remember, it's not just 5, right? Because that wouldn't work. You can't add a constant to a matrix. We multiply that to the appropriately sized identity matrix, which would be a 2 by 2, in order for all that addition to be defined. Okay? Let's do this part off to the side. When you're first learning about matrix exponents, sometimes it's tempting to say, oh yeah, I just square each entry in here if I'm squaring the matrix. No, that's not going to do it. In general, that's going to be that's going to give you an incorrect answer. Remember, the literal meaning of this is 1103 times itself. We have to carry out the matrix multiplication directly. Don't try to square all the entries in there. This is going to give me, let's see, 1 times 1 plus 0 is 1. This is going to give me a 0 down here. This will give me 1 plus 3, which is 4. And then I'm going to get a 0 plus 9. So, yeah, there we go. So I got 1409, okay? Which is not what I would have gotten just by squaring all of these entries. There we go. So that's going to be what I get here, 1409. Now for these guys, let's go ahead and do the scalar multiplication. -2 times this matrix is going to look like -2, -2, 0, -6. And then same thing here, multiply by 5, I get this. 5, 0, 0, 5. From here, it's pretty straightforward. I just do the addition and subtraction. So 1 minus -2 is 3, plus 5, that would be 8. 5 minus -2 is, 4 minus -2 is 6, plus 0 is still 6. 0 minus 0 plus 0, that's all 0. And then finally, 9 minus -6 would be 15, plus 5, that's 20. Okay. And that's it. Okay, so that's a matrix polynomial. These things have applications in a few different places. Right now, we're just worried about defining them. We're not really too worried about using them for anything quite yet. All right, so we established a theorem concerning exponents and inverses. That was the last theorem that we looked at. Now what we want to do is look at some theorems concerning transposes. So this is our theorem right here, 5 properties of transposes of matrices. It says if the sizes of the following matrices, A and B, are such that the operations are compatible, so A plus B would imply that A and B are the same size in order for that to make sense. A times B, you have to have the correct dimensions for that to work. All of these properties would then be true of these two matrices. Now, a lot of these are very easy to visualize. A, for example, what does it mean when you take a transpose of a matrix? Well, A transpose is the matrix that takes all of the rows of A and converts them into corresponding columns. But then if I take the transpose of that, it's going to take all of those columns and turn them back into rows again, getting me back to the original matrix. So it's very easy to see why this one's the case. It's not difficult to see why B, C, and even D are true. The transpose of a sum of matrices is the sum of their transposes, and so on. One that's a little bit more difficult to see is this one. And we're going to prove this one. I don't think your book goes through the proof of this. I think it proves one of these other properties, but this one I'd like to walk through a proof with you because it's a good exercise. The transpose of a product is the product of the transposes in reverse order. Kind of like how when we took the inverse of a product of two invertible matrices, the order of those matrices switched before we took their inverses. So how do we prove this? Well, let's walk through that. Let's suppose A is an M by N matrix and B is an N by P matrix. What this does is it guarantees that A, B is defined because the inner dimensions match. They're both N. So that would imply that A, B is defined and it's an M by P matrix. Remember, its result has these outer dimensions. Okay? But then what does that imply about the transpose of AB? Remember, the transpose of AB switches these dimensions. So AB transpose would be a P by M matrix. Okay. Also, B transpose would be a P by N matrix, reverses those. A transpose would be an N by M matrix. And so when we do the product in reverse order, we have a P by N matrix and an N by P matrix. The inner dimensions match again, and the outer dimensions are P by N. So this matrix here, B transpose times A transpose, is also a P by N matrix. Therefore, the matrices on both sides have the same dimensions. Remember, when we're proving that a product of, or when we're proving an identity for matrices, that one side is equal to another, we always start by showing that the dimensions of both sides are the same. So that's that first argument. The next step is to show that any arbitrary entry that I choose from the matrix on the left-hand side is equal to the corresponding entry in the matrix on the right-hand side. So in this case, it's tricky to do that if we use the definition of matrix multiplication given in the book. And I think that's why they avoid covering this proof in the book. But if we use our dot product definition for matrix multiplication, it turns out to be significantly simpler. So what we're going to do is we're going to let R1 through Rm be the rows of A. Remember, A is an M by N matrix, so it has M rows. And then B should have P columns. We're going to denote those C1 through CP. Okay? And I and J are going to be any integers such that I is between 1 and P and J is between 1 and M. Basically, this is just saying that I is going to be one of the subscripts for these columns. J is going to be one of the subscripts for these rows. Okay? So what I want to do is start with the matrix that's on the left-hand side, the transpose of AB, and take a look at its ijth entry. It's kind of a way of choosing an arbitrary entry. So what is the ijth entry of AB transpose? Well, the way that we defined transposes in the previous section is that the ijth entry of the transpose of a matrix is the jith entry of the original matrix. So that would be the same thing as the jith entry of AB. But what is the jith entry of AB? Well, remember, AB, that's matrix multiplication, and the jith entry of that matrix comes from taking the dot product of the jth row of A with the ith column of B. That's this, rj dot ci, right? So that would be excuse me, that would be what the ijth entry of this side looks like. Now what I want to do is look at the matrix on the right-hand side and find its ijth entry. I would like to show that I get the same thing. So looking at that, what is the ijth entry of B transpose times A transpose? Well, we know that the jth row of A is actually the jth column of A transpose, right? Because that's what a transpose does. It swaps this row for this column. And the ith column of B is actually the ith column of B is actually the ith row of B transpose. Let me write that in there. Okay? So from that, it would follow that B transpose, its ith row, is actually Ci. That would be the ith column of B, but it becomes the ith row of BT. And similarly, Rj would be the jth column. It started out as a row in A, became a column in A transpose. So that the ijth entry is Ci dotted with Rj. Now, back in the preliminary section where I introduced the dot product, I showed that the dot product is commutative, which means that if I have Rj dotted with Ci here and Ci dotted with Rj here, they're actually the same thing. They're equal to each other. So that proves that the ijth entry of the matrix AB transpose is equal to the ijth entry of B transpose times A transpose, which wraps up this proof. All of the corresponding entries would have to be equal to each other. Okay, kind of a good proof. It's a little bit more hefty as far as the proofs we've looked at so far, but it's far, far better than it would be if we didn't use dot products. It's way messier and not fun if we didn't go this route. All right, Another theorem. So I'm going to pause for a moment and just comment on this. If you haven't gotten a sense of this already, this is very much the flow of this class. And I think I mentioned it before, but there's plenty of computation for us to do. We've done some matrix multiplication. We found an inverse, which was computational, all that kind of stuff. But as we go through these sections, it's a lot of theorem after theorem after theorem. And that's what I mean when I say this class is more theory focused. It's developing all of these theorems and these results. So if you're looking at this and you're thinking, wow, I just talked about one theorem, I didn't do any examples with that, I just moved on to another theorem, that's kind of how this class flows. The homework is where you're going to get more practice on using these things. Okay, so let's talk about this one. If A is an invertible matrix, then the transpose of A is also guaranteed to be invertible, and its inverse is the transpose of the inverse of A. So this one is easy to prove from using the definition of an inverse. If I want to show that A is if I'm assuming that A is invertible, but I want to show that A transpose is invertible, then I simply need to find a matrix that can be multiplied to A transpose that gives me the identity. And this part of the theorem is telling me what that matrix should look like. So this side says the inverse of A transpose is the transpose of A inverse. This is the matrix that I want to attempt to multiply to A transpose and show that I get the identity. So doing that, if I multiply A transpose times the transpose of A inverse, notice I have a product of two transposes. We have this property that we just proved up here that says if you have a product of two transposes, it's the same thing as the transpose of the product but multiplied in reverse order. So if I apply that here, I can reverse the order of A inverse will now be on the left, A will be on the right, and I take the transpose of their product. However, A inverse times A is the identity matrix by definition. That's what an inverse does. And we talked about this when we introduced identity matrices. The transpose of an identity matrix is itself. So that proves that multiplying A transpose by this guy gave us the identity. In order to prove what we're trying to prove, I would have to do the multiplication in the other order as well to show that I still get the identity, which would then establish that this is the inverse of this. But the proof is so similar, I'm going to leave that part out. So you can do it if you want. It's all the same ideas. So that establishes this proof. Okay. So here we have this matrix A. A is equal to 2, 3, 2, 5, and what we want to do is find the inverse of A transpose. Well, according to this theorem, to find the inverse of A transpose, I first need to find the inverse of A, and then take the transpose of that. Well, we already found the inverse of this matrix in a previous example. We showed that its inverse is 5/4, -3/4, -1/2, and 1/2. So, by our theorem then, the inverse of A transpose is equal to the transpose of A inverse, which is the transpose of this. Main diagonal entries won't change, 5/4, 1/2, but the other diagonal will swap entries, -3/4, -1/2. That would be the transpose right there. Okay. If you want to confirm that this is correct, you can take the transpose of A, multiply it to this in both directions, and show that you get the identity matrix both times. All right. And looks like that's it for section 1.4.